This is an atom at work. Inside the star's incredibly complicated atomic-wide energy to send radiation through thousands of light years to our eyes. A star is a self-luminous body in space. It creates, by some complicated processes within the star, its own light and heat, that energy which we receive from. Contrast this self-made light with the reflected light that we get from the sun, from the moon rather, and the other planets, not from the sun, because the sun is a star. In fact, the sun is the only star whose surface we can see, because the sun is the only star that is near enough to us. All the other stars, no matter how big and how bright they may be, and we shall meet some strange ones later on, are so far away that all we can get from them is a single point of light which has just one dimension, distance, the distance that the light travels in getting to the star from us. Now, stars come in a tremendous variety. There are enormous stars. There are tiny stars. There are hot stars, and there are cool stars. And there are stars of almost every conceivable color. They are of such infinite variety that the task of cataloging them and classifying them would seem to be almost impossible. And yet it has been done, and done very well too, by two astronomers, Einar Hertzsprung and Henry Norris Russell. Now, they have made a diagram in which they are able to show every kind of star there is. And this diagram, of course, is called the Hertzsprung-Russell diagram. They set up this form by making a vertical scale which had to do with the star's brightness. Now, this vertical scale runs from brighter to fainter, down through the scale of the star's brightness, which are called magnitudes. Now, in order to simplify the comparison of the brightness of a star, the comparison of magnitudes, astronomy has theoretically placed all the stars at the same distance from us, a distance of 32.6 light years. And the star's brightness at that distance, it's called its absolute magnitude. And it is the absolute magnitude scale that Hertzsprung and Russell used, from the very brightest of the stars down to those which are extremely faint at the bottom of the scale. The horizontal scale, which Hertzsprung and Russell used, was based upon the spectral classifications of the stars, and which also means that it was based upon the star's color and the temperature. For here at the left, the stars are the hottest stars, blue stars, and they range from that point down the scale of temperature and color through all the variations of color until we get the fairly cool red star at the other end of the scale. Now, Hertzsprung and Russell spotted their stars. Wherever the characteristics of a star, for example, in magnitude, corresponded to a point on this scale, they moved in which the star fell as far as its spectral classification and temperature were concerned, and there they put a dot. Now, let's take this sample star of ours, the sun, and see how it works. The sun, we know, has an absolute magnitude of 4.5, a little fainter than fourth magnitude. Now, let's follow that line out until we come to the sun's spectral classification, which is the G, the fairly cool star. Surface temperature, incidentally, these are surface temperatures of 10,000 degrees Fahrenheit, not centigrade, Fahrenheit. So, put a dot where that temperature corresponds with that brightness, and there is the location of the sun in the Hertzsprung-Russell diagram. Now, as Hertzsprung and Russell placed these stars on their diagram, they found that the vast majority of the stars fell in this rather wide belt that curves across the diagram from upper left to lower right. So, since that did contain the majority of the stars, they called this the main sequence. And the stars that fall in this belt are called main sequence stars, and our sun is a main sequence star. Now, the main sequence stars, of course, range in size considerably. There are stars here which are 100 times as big as the sun, and stars which are 1/10 of the diameter of the sun. So we have this range of stars from about 100 million miles, or 10 million miles, 10 times that, 10 million miles to about 100,000 miles in the main sequence. And these stars vary, of course, in brightness according to their temperature and their size. Now, normally, a star is easiest to see when it is hottest. As an example, let's take a piece of metal, ordinary metal, anything will do, and put it in a dark room. It's cold. In a dark room, you can't see it. But if you heat that metal till it begins to glow, then you can see it, even though the room is dark. And the hotter that metal gets, the brighter it will be. It will go from red up through orange and yellow to white, and of course, by that time it would have melted, but nevertheless, the hotter it is, the brighter it is. So it is with the stars. The hotter the star is, the brighter it is if the size is the same. Now remember this too, that each square unit of surface of a star is giving out energy. Now, the more square units of surface there are, in other words, the bigger the star is, the more energy it gives out, the more light it produces. So if we have a hot, big star, it is going to be very much brighter than a small star of the same temperature. That is what happens. And this is the main sequence, from the hot blue giant stars down to the red dwarf stars. You might call these normal stars. Now, there are other kinds of stars. There are many offshoots to this. Remember what we have said about the unit of surface giving off energy. Now, we know that there are stars whose spectral analysis tells us that they are cool. They're not very hot. And yet they are bright. Now, what does that mean? Stop and think a minute. That means that there must be a great many units of surface working to produce the star's light. They're big stars. They are the giants. They are not in the main sequence. They are off the beaten track. They are bright, but they are cool. They must be big. Now, technically, a giant star is a star whose diameter runs from 10 times the diameter of the sun to 100 times the diameter of the sun. The sun's big. The sun's diameter is 864,000 miles, say 1,000,000 miles in round figures. All right, here's a star whose diameters start at 10 million miles and run up to 100 million miles. Think what that must mean. These are big. This is enormous. But wait, there are other stars, even cooler, intensely. These must be enormous, tremendous surface area. Here they are, these supergiants, whose diameters are more than 100 times the diameter of the sun. Now, we have a very good example of such a star, and we have a diagram which will show us such a star in relation to some other units which we know about. We have a picture here of a very famous supergiant star. This is the great red star Betelgeuse, the star in the upper left-hand corner of the rather irregular quadrangle of the constellation of Orion. Here is Betelgeuse. Now, what have we got inside of it? Well, a good part of the solar system. Here's the sun. Here is the orbit of Mercury, the nearest planet to the sun. Here is Venus. Here is the Earth. And here is Mars. Now, we know that the Mars is at an average distance from the sun of 141 million miles. And the diameter of Betelgeuse is very nearly 500 times the diameter of the sun, 500 million miles. That's big. That's enormous. And yet there are bigger stars. There is one star, we believe it to be the biggest star we know about, which is in the constellation of Hercules. Its diameter has been estimated at 6,000 times the diameter of the sun. That's 6 billion miles. Now, the diameter of our whole solar system is only about 7 billion miles at best. Here is a star which would almost fill the whole solar system if the sun were placed at the center of that star. Now, we've got one other very interesting star here. This is one we can't even see. It is so cool, it doesn't give off enough radiation to reach our eye. And the only way we know of its presence and of its size is because it has a very bright companion star going around it in an orbit. It takes this star 27 years to complete its path around the big star. And at times, it passes behind the big star. Now, the gases that make up this enormous star are so tenuous that they're almost transparent. And we can see this smaller star, which is quite bright, passing behind the big one. We know how long it takes, and we know just exactly how big that star is. We can get an accurate measurement here. This is 3,000 times the diameter of the sun, 3 billion miles in diameter. Those are the big fellows. They're tremendous things. They are tremendously distended, too. The masses of stars, that is the amount of material they contain. Incidentally, mass is what weight is on the Earth. Your weight is the pull of the Earth upon the mass of your body. So the masses of stars don't vary very much. There are few, if any, stars which have a mass which is more than 100 times the mass of the sun. Now imagine a star with 100 times the mass of the sun, but 1,000 times the diameter of the sun. What's happened to that material? It's distended, it's blown way up. This is a bubble, this is nothing. Here is a red-hot vacuum. And only by contrast with the utter emptiness of space around it can we see such a star at all. These are the supergiants, tremendous, unbelievable stars, and yet there they are. You can't get away from the evidence. Now, on the other end of the scale, there are extremely hot stars, but faint. Now, what does that mean? Think of that again. Faint stars, but hot, should be bright, but there are very few square units of space working here. These are tiny fellows, little bits of things, and they are in the hot category spectrally, but in the faint category by magnitudes, and they are down here, and these are the white dwarf stars. And if you thought the big ones were unbelievable, think of these. Remember, the mass of a star does not vary too much. Here we have a star which must have the mass of the sun the size of the Earth. Squeeze the sun down until you get it to the size of the Earth. It still weighs the same. Its mass is the same. How terribly condensed it must be. The first of these stars to be discovered had such a density that a cubic inch of it, a little bit of a cube, an inch on a side, weighed a ton. And the champion of these stars, of this class of stars, is one which has a density 36 million times the density of water. It would weigh 36 million times as much as the same amount of water. It weighs 620 tons per cubic inch. Now, how can this happen? Well, in order to find out about that, we've got to go back to the basic unit of matter, the atom. The atom which once was believed to be indivisible. We know better now. We know that the atom has an extremely complicated structure which is divided into two regions. Here is the nucleus, the center of the atom, made up of particles called protons and neutrons mainly, with a few other particles between. The outer regions of the atom are made up of electrons. Now, all the mass, all the weight, if you will, of the atom is in the nucleus. There is none in these electrons. And the electrons move about the atom in orbits, very much as planets move about the sun, but these orbits go in every direction, whereas the planets of the solar system move in practically one plane. Now, it doesn't take very much energy to detract, to tear off an electron from the rest of the atom. The energy in the center of the stars is ample for that. For in the interiors of stars, we have temperatures which run into the millions of degrees. That's plenty to do this. Now, most of the atoms inside the stars have lost most of their electrons. In the white dwarf stars, they've lost all of them. Now, normally, two atoms cannot get closer together than the limits of the orbits of their electrons, like this. You see how much empty space there is there? With the electrons gone, the nuclei of the atoms can get close together. You've lost volume, you've lost space, but you haven't lost weight. That is these terribly dense, heavy stars, these white dwarfs. Now, the Hertzsprung-Russell diagram again, the position of the stars on it and the way they are placed gives us a hint as to the possible evolution of a star. Certainly, the human race hasn't been here long enough to see a star go through its birth processes, its coming of age, its maturity, and its death. But we think we can see young stars and middle-aged stars and old stars. And while we can't see dead stars, they may be there. And we believe we can reconstruct the processes of evolution from this evidence. Now, we also find that all of the stars, all of which can be placed on the Hertzsprung-Russell diagram, can also be divided into two enormous overall classifications, which we call population 1 stars and population 2 stars. Population 2 stars are generally the hot blue or white stars and are found in the upper section of the main sequence. Population 2 stars are found everywhere else. The red stars, the cool stars, the white dwarfs, and all the rest of them. And there is a reason, a definite reason, for the difference between these two stellar populations. Population 1 stars are found in the regions of the great star organizations in which they lie in a certain specific place. Now, we know that these great organizations of stars, these galaxies, we live in one of them, the great Milky Way system is a galaxy, are not only made up of stars, but there is a great deal of dust and gas in the space between the stars. This dust and gas is not evenly distributed over these galaxies. It lies mainly in the outer regions of the galaxy and in a central plane. Let's look at a picture of such a galaxy for a minute. This is a typical galaxy seen edge on, and we can see this dark line cutting across the galaxy. There are stars there too, but there is also a great deal of dust and gas making this line. Now, in the central part of the galaxy, in what we call the nucleus, it's bright. There are no dark obscuring matter there, and there are stars without much dust and gas. Here's another view of a galaxy. This one we are seeing in plane, flat, you see, almost. And here is the nucleus, bright, stars. You can begin to see a little bit of darkening there, but out here in the disk where the arms are, there is lots of dust and gas scattered in among the stars. And here is where the population 1 stars are found. Now, these population 1 stars have a normal growth. They start small and red, and they go up through all the colors and get hot and blue, a very even and fairly prosperous existence, because they are in the region in which their vital fuel is found, and this fuel is hydrogen, the most abundant element in the universe and the simplest of all atoms. The hydrogen atom has one proton in its nucleus and one electron orbiting about that proton, and a proton is the nucleus of the hydrogen atom. Now, where these stars travel, in the regions of dust and gas, there is an abundance of material, and these stars move through that dust, sweeping it up, replenishing their vital forces. Great celestial filling stations we have here. These are the population 2 stars, the stars that live a normal, straightforward growth. Population 1 stars don't have as easy a time of it. They start out in the normal way. And when about 15% of their own hydrogen is used up, they're stuck. There is no dust and gas where they are. They can't replenish their supplies. They have to live on their own fat, as it were, eating up their own hydrogen. This is fine until about 15% of it is gone. Then the process speeds up, and the star begins to change. It swells, it grows in an effort to maintain its energy and its heat. And it gets big and red and cool. And then when about 60% of it is gone, comes the critical time in the star's existence. It may collapse suddenly. And in collapsing, a tremendous heat is generated. And the star sometimes explodes and blows itself to pieces. Sometimes that collapse continues, and the star winds up as one of these terribly dense white dwarf stars. Now, I spoke a little while ago of our sun as a sample star. We are pretty well aware of the processes that are going on in the sun, a series of complicated thermonuclear reactions. And we have worked up a little graphic sketch here to show in a measure what happens there. Now, there are in this reaction involved, first of all, one normal carbon atom and 4 protons, the nuclei of hydrogen atoms. Here we have the normal carbon atom. It is struck with terrific force, force enough to bang that proton into the center of the atom by a proton, the nucleus of a hydrogen atom. that affects a terrific transformation in this carbon atom, changes it into a variety of nitrogen. Not the common variety that we know that is in our air, but an unstable variety, which has a lifetime of the minutest fraction of a second, and that changes of itself into a variety of carbon again. A different variety, but a stable variety of carbon. And this fellow is struck again by the second of the 4 hydrogen protons involved in this process. This affects another transformation, changes our carbon atom into another variety of nitrogen. This time it's a stable variety. It remains as it is until it is struck by the 3rd of these protons and is changed then into a variety of oxygen, which is an unstable variety of oxygen. So it changes of its own accord in a minute fraction of a second into another type of nitrogen. And along comes the 4th proton, which smashes into this last pure abused nitrogen atom, and what have we got left? We've got the original carbon atom that started the whole thing and went along for the ride and is ready to start it over again. We have a new element, helium. And what has happened to the rest of it? It's being carried away. The mass has been lost. You see, here goes the ghost, we might say, of these 4 protons. Now, in the sun, this is going on all the time. When I speak of 4 hydrogen atoms, you can multiply that by anything you like, because here is what happens. Every second in the interior of the sun, the temperature between 30 and 50 million degrees, 564 million tons of hydrogen are transformed by this process into 560 million tons of hydrogen. Now that's a loss of 4 million tons of the sun's mass. That mass is converted into energy. And up till a short while ago, we didn't realize that mass and energy were interchangeable. And the formula for this interchange was given to us by one of the greatest scientific minds that ever lived, Albert Einstein. His formula is E equals mc squared, as you see here. Now the E is the energy, the production of this transformation. The M is that loss of mass, that 4 million tons a second, those 4 little hydrogen protons. C is the symbol for the speed of light, the speed of energy. We square that C, and we multiply that tremendous figure of the square of the speed of light. Light travels 186,000 miles a second by the loss of mass, and we get the resulting energy. This is that terrific energy produced by the sun and in the same measure by all of the stars. Now, there you have the 2 general populations. We've got the main sequence, the normal star. We've got several strange offshoots, but there are still other strange stars to come, too. There are stars whose light is not constant, variable stars, because their light does vary. And these stars vary through some interior convulsion of their own that we do not understand. And there are types of variable stars which change with extreme regularity. They are small and faint. They swell and get bright and cool, and they shrink small and faint again. And they pulsate up there like great hearts in the sky. Some of them do this with extreme regularity. And these regularly pulsating variable stars have given us an invaluable means of measuring the distance in space. For there is a direct relationship between the length of time it takes these regular stars to go through their cycle of pulsations and of light changes and their absolute magnitude, that intrinsic brightness of a star. And if we know the absolute magnitude, we know the light we see, the distance is the result. And these intrinsic regular variables are yardsticks of distance. There are irregular variable stars which remain faint for a long, long time and then suddenly blossom into brightness for a little while and go back to faintness again. There are stars whose cycle is the opposite, which remain bright for a long time and drop for a short while and are bright again. There are irregular variable stars, all kinds of variable stars, and they are still a puzzle. We are still working to find out what they are. Then there are stars which have reached this critical stage in their development. Remember when 60% of their hydrogen was gone and almost anything could happen? Such stars have sometimes met with a celestial catastrophe. They have exploded. Now, in the days long gone by, such a star, of course, at its normal brilliance, was not visible without a telescope. When they did explode, rising sometimes to hundreds of thousands of times their normal temperatures, the star became bright. You remember, hot stars, bright stars became much brighter. And people saw them then in that stage for the first time and called them new stars. Now, we know they weren't new stars. They were old stars, been there all along, but which had met with this terrific celestial catastrophe. Now, that's still going on. There are about 20-odd such stars which happen every year. And they are recorded on astronomical cameras and so on. Very few of them are bright enough even for us to see. I mean, we still use the ancient term for such stars. Here is a working photograph of such a sequence. This is the kind of a picture an astronomer uses. He doesn't deal in the positive pictures. Astronomy works from the negatives. This is a nova. For nova is the Latin word for new, and they're still called new stars even though we know they're not. Now, here is a picture taken of this star way back 75 years ago. This is the way it's been. It's a normal, apparently peaceful star. Then on the 3rd of June, 1918, something began to happen. Here's a picture of the same star taken that night. On the 7th of June, 4 days later, the same star had increased in brightness about 1,000 times, probably in temperature. On the 8th of June, it really let go. This must be 100,000 times as bright as it was then. These are the novae, strange stars. We don't know what's happened to them. They've exploded. There have been 3 cases in the history of mankind when a nova has become so bright that it casts a shadow at night. And these are the supernovae. We have one about every 500 years. We're overdue for another one right now. Now, let's sum up a little bit. What have we found out about the stars, this tremendous variety of stars? Here is a chart which gives us a kind of a run-through of what we've talked about today. Sizes, all sizes, from supergiants, unbelievably big, to the white dwarfs, unbelievably small. In colors, from red, orange, blue, white. Then again, the red dwarfs and the white dwarfs. White, really white. And temperatures, big ones, cool, giants, warm. Main sequence from hot to warm. Red dwarfs, fairly cool. White dwarfs, hot but faint because they are so small. The 2 populations, the hot blue stars in population 1, the well-fed stars, all the others in the starving population 2. That is just a fraction that we know about the stars. If we all that we know, they'd still be 99% mystery.
This is National Educational Television.